By the way, how do you like this paper?
Sorry.
How do you like this paper? How do you think about this paper? This paper is short, right? It's not a difficult.
Yes, but its type is somehow different. For example, previously we had it was somehow more computative, like as, for example, knowing how to use flex function, or the type of optimization was somehow different.
Right. Originally, we have 3 papers on imitation learning. However, finally, we can only present 1 paper in class. We also have another online presentation from Hammered, and I will send a link to the students later on imitation learning on robotics, and then we can check the paper as well. Yes. So I think everyone is busy this week. So I mean, right now we only have 6 people here. Maybe we can wait for one more minute and to see if we have more students joining us or not.
Sure.
So hello everyone. So I just want to have you finish your final paper or not? I mean, for students in the class. I mean, how do you think about the final paper you're working on right now? Because in the system, in the Canvas system, I can see some submissions already. So some teams have submitted the paper already to the Canvas system. So, I mean, it's a reminder for you. You need to start to work on them earlier, right? Then you don't need to wait until the last minute to submit the paper. Okay, so maybe we can start. So hello everyone. Today we'll discuss the last paper for this quarter. And this paper is very different from the other papers we discuss in class. This one is about robotics, and we try to use the imitation learning to study, to control the robotics to perform some like actions. And so imitation learning right now is very popular in robotics studies, and we have 3 papers on imitation learning originally. However, finally, we can only present 1 single paper on imitation learning in class. We also have 2 other papers which is available in the schedule spreadsheet. And the presenter today will be Arifa, right? And then Arifa will need a discussion for us for this paper. Yeah, Arifa, I can give the time to you. You can start when you're ready.
Thank you. Hi, everyone. Good evening. I'm Arifa, and I want to talk about imitation learning method from MPC for Quadrupedal Multi-Gait Control. Okay, this paper is somehow different from the previous paper we have in a way that it works with control problems, and it is somehow working with how we can optimize it in order to we can have a better control. And also the type of the application that we are working on is robot controls. So the data, it would be somehow different. In robotics or maybe a mechanical engineering application, we have a type of data which can be noisy, and the type of application is controlling. For example, we have a robot and we want to give some command to it to do something, for example, walking, for example, or have some specific movement. But the main challenge is that this problem is somehow hybrid, and also working robots control has a lot of complexity. And another important thing is that it is an onboard real-time control. And for this application, in previous literature, they're working on learning policy to control inputs online. Another method is that using optimal control framework to find control inputs with constraints and also do performance optimization. And by this, we can have training of feedback policy as an offline. And then another important method is that using model predictive control, which can benefit from data-driven and model-based approaches. But quadrupedal robots in different environments needs to adapt different type of gaits. For example, it would work on uneven ground or slippery ground, which needs dynamically stable gaits. Another interesting application and another interesting approach could be reinforcement learning, but it's maybe not good for this application because policy may converge to a single gait, but we need different gaits. In this paper, they're working on a learning algorithm for training a single policy for different gaits, and they imitate multiple gaits of a walking robot. The main idea is that extend MPC-Net and using imitation learning approach, which guided by model predictive control. And also for represent the policies, they employ mixture of expert networks. The specific contribution of them is that suggest some loss function, which is a new Hamiltonian loss function. Its localization, it's so good on men's experts. And also they provide some guided loss function, which allows incorporation of domain knowledge for an improved expert selection strategy. And this their method leads to more robust policies which compared to previous methods, and it has high performance execution too. Let's see some preliminary knowledge about their proposed method. First, consider a model predictive control, which is an optimal control problem. You want to optimize some objective function phi regarding states x in each time step and also input u. And for this, you can consider corresponding Lagrangian and also control Hamiltonian to make it more robust. And after that, another thing you should know that is MPC-Net. MPC-Net is an imitation learning approach guided by model predictive control, and it's working using different approaches in a way that it wants to minimize some control Hamiltonian, which its objective is to some principle of optimality. The main idea of MPC-Net is imitate MPC problem that I talked about it before by minimizing the Hamiltonian. And this Hamiltonian function considering corresponding control inputs, which can be important for control applications by a parameterized policy. And then by finding a locally optimal control policy, it can be simplified to minimize function. And then it motivates a strategy for finding optimal parameters. And regarding computing these optimal parameters, we should consider it regarding some distribution P, which is time state space that it is visited by optimal controller. Then MPC loss function L2 is defined by this, which H is a Hamiltonian function. And regarding that, we want to compute we need to compute gradient of loss function. And for this, we're using SL cube, loss solver, and backpropagation. Let's see two main new Hamiltonian loss function and guided loss function that proposed in this control method. The log partition loss function introduced a loss function, which is inspired by least square setting and main loss function. L3 is the result of this point of view, which beta is inverse temperature parameter, and this is a bias term. After that, each expert has a weight pi, which can be seen as a prior probability, and each expert I can minimize the Hamiltonian at current observation. Then we have a posterior probability that computes like this, and using this, we define L3 loss function. Other than these, they define some guided loss function. This guided loss function has an idea of using learner with providing learner with domain knowledge and have some advantages of expert selections. Also, it influenced by learning the cheating idea, learning by cheating idea. So we have guided loss function is the sum of LE, which is an expert loss. This expert loss is defined by L1, L2, and 3 that we talked about it before, and LD, which is domain knowledge loss. And also lambda is a control that can compute by relative to importance of both loss. It can somehow arrange how important these two loss functions are in respect to each other. This guided loss function can be considered in hybrid systems and also in expert selection. For example, it can be used in model selection, in optimal control problems, and also it can consider gait or model selection, mode selection too. And also, it's good for optimization method and considering domain knowledge, like as considering some qualification of train or command speeds. It leads to mode schedule MT that returns the active mode I at every time, because we can have several active mode in at each time. And also its generalized case can be mode selection, which this mode selection can be considered in different observed states. And also the empirical probability to observe mode I is considered in this guided function. And for computing this, we're using maximize the log likelihood, which is equal to minimizing the cross entropy, and incorporate domain knowledge, experts and modes. And for this, we should consider that we have two types of men: mixture of implicitly localized experts, which using competitive process to localize the experts like as L2 function and L3 function. And another one is mixture of explicitly localized expert, which is assigns the experts to pre-specified cluster, like as loss guided loss. This method is somehow different from just assigning some hard coding to the experts according to some heuristic and training of separate networks. The specific thing about it is that it considers modes and their probabilities to be a function of the observation. For example, consider that you have different gates or some gating network that can learn to deviate from some heuristic. In this case, a mode schedule that considers the hybrid system can be used and adapt the expert selection to can deviate from this heuristic or consider current observations. For implementation of this, we should regard some things. For example, consider the difference between trot and a static walk is something like that. It is trot moving and it is a stat walk. They considered ANYmal control in this implementation, which is a hybrid system, and it has distinct switches for each contact configuration. And fits are constrained to have 0 contact forces in swing phase, and also the velocity is 0 in each contact phase. For modeling the robot, they consider Kinodynamic model for MPC. It has 24 states like as base pros, base twist, and joint positions, and also 24 inputs, which are foot contact forces and joint velocities. And also optimal control cost function defined as this, which x are positions, and xt is the desired state trajectory that should be tracked. And also we have two types of gaits, trot and moving the diagonal legs together. And also a static walk and also moving one leg at a time is another one, which including the stance mode. And we have 7 control modes. There's a gait parameterization that we considered. We need gait parameterization because just considering absolute time and current state is not enough, and it is difficult to learn policy to infer which legs should be moved at the next time. So we consider some phases phi for scheduling our movements. And it is phases, it is left front, each of these elements referring to each leg phases. And phi is defined as this formula, and yeah, based on whether we are in the swing or contact, we have different values. And also in swing, we have somehow some sinus or some periodic function, because in each movement, we have some similar actions. And for each leg phase phi, we should learn asymmetric between lift-off phases, which are touchdown phase and time derivation of phi, because time derivatives of phi shows difference between phases that we can use it for predict the next state, which is the next action. And also we should capture different swing speeds too. Also, movement is somehow some relative action, so we should do tracking. For reference tracking, we replace the state x in the policy with a tracking error, which called the relative state, and defined as this. And theta is the current orientation of the base in the frame that we are computing our movements. And also my matrix type B, theta B, transform the pulse error from the world into the base frame. We need some policy training and development invariant because we want to compute absolute orientation. For policy architecture, we consider main architecture for the policies. We have 8 experts, which also compute by a multi-layer perceptron experts, and multi-layer perceptron experts gating network with a softmax output activation. We should somehow ensure that the expert weights P are positive, and some of it should be 1, can come done by some normalization. And train policies with epsilon 12 is enough, and their experiment shows that there is no advantages if we add more experts. There are more common softmax embedder correspond to the concept of single responsibility. So in considering issue handling of expert selection with the newly introduced loss functions L3 and LG can be computed too, to know which one is better. For main architecture that we have, or somehow mixture of model of policy, we have a group of experts that have some input to our model, and also there's a gating network that we sum up for finding the next value. And for training, we have asynchronous values in asynchronous computation in policy search and the multi-threaded data generation. And also MPC-Net established different gates. We have multi-threaded data generation, ensures amount of data that would not have a bottleneck. And it's a good news because in most of the application of data-driven one, we have bottleneck for data. And data are generated by each end thread. We have a number of jobs per data generation run. And for each job, we start from random initial state. And with a task to reach a desired state XD, we have some rollout length T. In each loop, we save data and forward simulate the system by the next time step delta T, and we avoid storing data that have similar information content. So for do this avoidance of extend data, we do downsampling and only save the nominal data. If the generation ROS has completed, data are pushed into the learner's replay buffer of size n. And in every learning iteration, we have a batch of B tuples, which are from the replay buffer. The empirical cost function that they used in their training is computed as this, which is gradient descent step will be computed for parameter space using Adam optimizer. For the evaluation, they monitor the training progress and as a substitute for a validation set. Also, they compute the following metrics: the average constraint violation, the incurred cost, and the survival time, which is the survival time computed as the time that we had until we had some failure. And the systematic of MPC-Net training procedure is as follows. As I said, there is some data generation and there is some policy search. In data generation, we have some threads and some number of jobs. They pick some random job and compute optimal policy for them. They then get auxiliary terms to do computation of these parameters and then simulate it for some delta T time to compute pi. In this step, somehow some iterations to compute all of the jobs and all of the threads. And after that, we have some policy search, which we done asynchronous with this data generation. We have some replay buffer, which sample random batch and then compute empirical cost J, and then gradient descent step. Also, the monitor metrics that for computing pi is number of constraint violated, and also incurred cost and survival time. For deployment step, they are using some learned policy, which replaces MPC in control architecture. For controller, they consider mod scheduler and also the current state X, and also for some desired state XT, this desired state XT generated from the user comments. And then relative to state XR and generalized time T would be assembled to compute the policy network. Then Kinodynamic control inputs U, which inferred from the learned policy using Onyx runtime simulator. And also the whole body controller computes the torque commands that needed for Kinodynamic model. So we have some input and then policy module that goes to the system. The results computed by two main indicators: survival time and number of constraints violated. They used Ablation Study and considered generalized time T and the new loss L3, which help the MPC-Net algorithm to find a better policy. So the purpose of ablation study is that to find whether generalized time t and new loss function that they developed can find better policy or not. Also, they studied and compared L2 and L3 loss function to find whether which of them has lower number of constraints violation and faster increase in survival time. And as you can see, L2 is above in constraint violation. So the threshold of constraint violation in L2 is more than L3, but survival time at the first has somehow higher growth in L3, but at the end they converge. And also when they compare BC and MPC-Net, they find that during each iteration, they can converge when they get about 100 type number of iterations, but BC has more number of violations. And also, survival time of MPC-Net is above the BC in all of the times, which seems that it is so better. And in considering trot, static walk, and both movements, we see that trot is somehow has more violation, which is makes sense because trot is harder. But we have some spikes in the number of static walk violations. And other than these, by considering survival time, we see that survival time of both movements are somehow similar, which seems that this method is more stable because trot is somehow more complicated movement, but both of them have similar survival time. So our robot is so stable that's in a way that it can handle trot and static walk in the same way. For benchmarking, as I said, MPC-Net shows that greater robustness by learning from the Hamiltonian, because we see that survival time of MPC-Net is so better in all of the cases, and it has constraint violation less than BC. And then it said that the constraint can consider and ensure physical feasibility. So we can, by this loss function, it is feasible to have such a model and such a movement of robots. And compared to MPC-Net achieves similar survival time. In this table, you can see survival times of different methods in different Z scales, and you can see that MPC-Net has more survival time, which is somehow similar to MPC-2. And by replacing the Hamiltonian and the bias term in L3, we can have normalized mean square error from the model predictive control commands that's computed in this table. And for robustness, they consider rough train in racing simulator, and also they command them to walk forward for at most 20 seconds, which it's not seems too much 20 seconds, because as you see the video, 20 seconds is not too much movement. So in my opinion, it needs more time of evaluation. And measure this by measuring survival time is important because if robot crashed, it can hurt. For computing, considering this, the policy trained with MPC-Net is outperform BC in survival time of rough terrain. But they said that they didn't consider it in training data. So it seems that by the previous training data, it can handle different slippery or for example, rough terrain. So their generalization of model sounds good. And for multi-gait policy, the interesting thing about this method was that single policy can learn multiple gaits. So it's good for handling different tasks, for example, or different types of movements. And they had high performance execution, and multi-gait policy, similar to single gait policies, can be handled, which is considered by constraint violation and survival time that we talked about it before. Other than this, it is the expert weight for different tasks. So this peaks means that we had some expert weight at some time, which can, as we see in the next video, we can see that how some experts push the robot to do something, and we can see how it affects their movement during time. It is the simulation, it is the hardware, and you can see their feedback is somehow similar, but just for changes between trot to walk, you can see somehow different changes in states. They said that they provide hardware evidence, and their hardware evidence is their movies. So let's see their movie and talk about, and by this we can have some intuition about how stability works, how robustness works based on the pushes or the expert movements on the robot, and also how generalization can work in different transition between different states of movements.
As shown on rough terrain, which was not part of the track.
In their benchmarking, they considered behavior cloning and MPC-Net, because behavior cloning was one of the benchmark in this method. And but if, for example, the robot falls down, it means that they miss their survival time.
Data, MPC-Net outperforms behavioral clone. In addition,
as you see, their plane of movement is similar, but the survival time of behavior cloning was so smaller than MPC-Net.
Compared to real-time MPC-Net policies achieve similar robustness on rough terrain. This robustness transfers to hardware.
Now you can see that experts tries to somehow give some feedback, maybe negative or positive feedback to the robots to somehow guide it to some movements. And as we see, the feedback of robots based on their forces, it's somehow positive that can consider its balance. So they consider it as a robustness.
The robust policy can also execute multiple gaits. As we intended with our approach, a single policy can learn several gaits, such as trot, as shown before, as well as static walk and pose control, as shown next. To demonstrate the generalization,
and also the most important thing maybe would be how robots can consider some policy for transition between different types of movement, from walking to running, or for example from walking to trot or something like that. They consider it as a transition between gaits, and as you can see, this dots means that which gait, which element or which phase is active, and they said that as we have some stability between different movements, so it can be generalized easily.
we let the policy alternate between the learned gaits, although the transition was not part of the training data. Finally, we tested in simulation how our method scales to more than 2 gaits, and added dynamic diagonal walking to the multi-gait training.
Okay.
As shown,
and as a conclusion, we found that the performance of their method can be improved if each expert of a man has been specialized for some movement or for some loss function. And controlling one mode of a hybrid system, such as watching robots, can be impactful in this method, and also introduce new loss function for a single and multi-gait policies is beneficial, and achieve this kind of expert selection behavior too. Their benchmark considering behavior cloning, original MPC implementation, and various different rough train scenarios, and validate approach on hardware. And also they consider single learned policy can be replaced its teacher to control multiple gaits. And in my opinion, as a future works, some complicated scenarios can be considered. For example, how in real time, for example, we have some real-time complexity that can be considered for a more complicated methods or complicated scenarios, and also how to avoid unsafe situation. For example, based on the previous movements, we can have some unsafe situation for the robot, which can be harmful for it. But how we can avoid this, because it's considered survival time after the robot fall down. But in my opinion, it's important to predict it and avoid it. And also how they can recover unsafe situation. For example, we have some robot that fell down, how we can recover it to have can robot stand up and continues its behavior, action, or its previous action or its previous movement. And there's a lot of extended scenario that we would have other than trot and walking. Its generalization based on 2D method, it's good, but in real world, we have more complicated scenarios that would be considered. There's some questions in the chat. Yeah, that question. ETH is very famous and they work on robots. Besides in this paper, you may also refer to their YouTube channel for more research works. I really enjoyed this paper because my understanding or my experience based on artificial intelligence, reinforcement learning, or something like that was based on some tag data or some non-hardware data that had different challenges. But this type of paper somehow changed my mind about different important challenges that can be considered in handling robots or a control problem. Is there any question or some future works or some ideas about this paper? I am interested to discuss about it.
Yes, so any question from the student?
Yeah, I have a question.
Sure, go ahead.
Yeah. For this robot and compare with the Boston robot, you know the Boston robot dog and the
Yes.
robot can running. And how do you feel about this one? Because compare the Boston one, looks like this one is not so
Yeah.
advanced.
Yes.
I cannot find how maybe they can publish the paper, but
Yeah.
the product may not as good as the Boston. So
Yeah.
how do you feel about that?
Yeah, I see. Honestly, I don't know the methodology that Boston Robot's using. I know this robot from about when I was in high school. So I think they are using more classic methods for controlling their robots because at that time there were no deep learning. But I think this paper gets more popular maybe because it is using imitation learning or, for example, using some more somehow different from classic methods. But yeah, if we just want to consider the advancement in Boston robots, there's more better, and it has better achievements. But the main important thing is that how many years they use to build such a robot. I mean, for example, I know this robot from many years, at least, for example, 10 years ago. So I think, yeah, maybe this paper could be different because of the method that it's used.
Thank you.
You're welcome.
Yeah, for this question, right? So, I mean, for robotics, this area is very old, actually. The
Yes.
conventional paper or works on robotics, the mainly focus on the conventional controlling scenario. Right? They're not based on machine learning or deep learning, actually. And this paper try to incorporate machine learning or imitation learning into the robotic controlling, right? So actually, I'm also working on robotics right now. I mean, so the main reason I have some papers incorporating to the schedule exploration is because I'm also working on robotics. I can show one of the robots I'm building right now. I'm not sure if you can see it or not. It's also a dog, but right now it's still a demo, right? It's a small one compared with the one that's shown in this paper. And this one, I mean, so to build a robotics, I mean, to build a robot which can work actually is very hard. I mean, you need to build a hardware. At the same time, you also need to control, I mean, use some devices to perception the nearby environments, do controlling, do reaction, and so forth, right? So building robotics from the scratch, I mean, is much harder than writing one single paper. So actually, if you can build a robot out, generally you can probably publishing more than 10 or even 20 papers with no problem. So it's a very difficult area, to be honest. So, but we don't have much time to have discussion more papers on robotics in this course, right? We only have one paper here, but I think robotics is area is a more challenging area, and at the same time, there will also be lots of opportunities in both research as well in the industry in the future years. I mean, many complaints besides both dynamics. We also have so many complaints like Tesla. They're also building robotics right now, actually, right? So this area has lots of opportunities. Besides self-driving car and robotics have more wider application in the future. But this area is also very difficult. Yeah, so any more questions from students?
I have a question about like the Hamiltonian that they keep mentioning. I think that requires a little more background knowledge in like classical robotics, but like, do you have a like an intuition about like what the Hamiltonian stands for? I mean, the paper says it's like about optimal controls, but like, do you have an intuition what it's about, like what it means to optimize an Hamiltonian of a control problem?
I don't have any rich background about Hamiltonian function or how it can affect. I'm not sure, but I think in ELM machines, they also use similar optimization to compute the proper weights for neural networks. I don't know whether this Hamiltonian has any relation to Hamiltonian distance or not, but let me bring the proper background. Yes, for this Hamiltonian, they're using Lagrangian and also control function. What type of intuition do you looking for? I mean, that's for example, what it means or how it can be improved, or I'm not aware about the deep intuition about it, but it somehow considers some less Lagrangian function and also use SLQ algorithm. It is somehow some deterministic method, but as a part of it, it considers some backpropagation to compute V function too. Yeah, but knowledge of linear algebra or something like that maybe helps to extend it.
Yeah, all right. Yeah, it probably requires a lot of background information in robotics too, just like to understand what, like, I mean, I think it goes to like control theory a little rather than. Yeah,
yes, but rather than this, I think linear algebra can help too.
All right. Thank you.
You're welcome.
Yeah, any more questions from students? This is another paper. I mean, this is another chance for you to ask questions.
One thing I'm curious about for this paper is that the insight seems that having dedicated experts for each modality of the control problem or each gate seems useful. But also, I don't have a background in control theory, so I found this paper very dense. But based on the reading, I think it seems like they're using some loss functions that explicitly encourage the specialization, and it results in improved performance. But I'm wondering if the specialization is so helpful, is there a way to formulate the task such that the specialization is learned just through a simpler task objective? Like you don't have to explicitly say that this expert should learn this particular modality or something like that. I'm talking about the cross entropy losses in 22 and 23. I don't know if I'm interpreting them correctly though, so I'm curious for your take on that.
Yeah, I see. I think the main, this type of algorithms, I'm sure that they cannot automate it as a whole. If they could, they didn't do this. But I think automation needs to do a step by step. For example, when we had some recommender systems, or for example, chatbot, at first we had some predefined chat, for example, some simple question. And I think they have similar things in their mind to can build such a model using experts. And yeah, just a part of it would be automated. And then at the next level, maybe they can consider experts on how to automate it.
Yeah, thank you. It reminds me a little bit of like multi-head attention, and I don't think there's any like diversity or specialization encouragement that's used to make the heads diverse from each other, but they learn, different distance senses kind of on their own because it's useful to the task. So I'm wondering whether that maybe there's a formulation of this task where the expert specialization emerges naturally versus having to be encouraged with, multiple different like loss functions or different parts of the objective. So
yeah, and the interesting thing is that a loss function doesn't have a lot of complexity. They have just bring different ideas and come up with them. Yeah, and yes, but I think the main thing that makes it more harder maybe is that it is somehow I mean that my main question was before what, but considering what you said, it seems that it is somehow under control of some classical formulation and somehow data-driven methods can handle it. Why they didn't consider that? I think the main important thing is that they need some near to optimal method to can have a stable robot. Because if because they cannot recover unsafe situation, so they cannot search a lot to find some optimal, and because of that they're using some experts to have some good simulation of what they want and then follow that. I think the main issue of this problem is that they cannot recover from many different situations, so they need some experts.
Yeah,
At least
makes sense. Thank you.
You're welcome.
Yeah, any more questions? So if there is no other question, then probably that's it for today. And so thanks so much, Arifa, for the talk. The presentation is very good, and it provides us with lots of information for this paper. We incorporate this paper into this course. The main reason is because for the conventional robotic studies, they have one saying like the controlling is dead, because the conventional controlling scenario generally dominate the current robotics control right now. So, and when we try to incorporate deep learning or machine learning into controlling of the robots, actually it's very difficult, it's hard. You also can see, I mean, conventional like reinforcement learning, even right now, the imitation learning, the controlling scenario, I mean, this quality is still cannot be compared with the conventional controlling scenario. I mean, in terms of performance. But there would be lots of opportunities to incorporate deep learning or machine learning into robotic studies in the future. And we use this paper to use this one as like a window. We open one window for you to see there will be lots of opportunities for you to explore in the future about robotics, to combine robotics with deep learning. I'm not sure if anyone are working on robotics or not right now or not. If you are working on this area, then you can see some opportunities here, and you can continue to your research on this area, right? And this is about this paper. And because right now we still have some time, I mean, this class is the last class we have for this quarter. I'd like to thank you so much for your efforts and the time devoted to this course. I mean, this course you can see is very different from other courses. We have so many new papers. To be honest, the majority of the papers we discuss in class are also new for me, and I also learn a lot from the papers. I don't know how to normally read the papers. Personally, I prefer to print the papers out. And I can see we have over 6 stacks of papers presented in class, discussing class. So it is even thicker than a textbook, right? So we have learned a lot. We have read lots of papers in this class, in this course. And at the same time, I also hope you can learn something useful from the papers, because they cover different areas related to deep learning. We discuss conventional deep learning. We also talk about computer vision, natural language processing, graph learning, recommender systems, and also right now the robotics. Right? So you can see deep learning has a very broad and also very wide applications. You can try to incorporate deep learning into your own research, into your own projects as well for the future. Right? So I hope you can learn something useful from this course. And at the same time, the paper we select for this course is also very limited. We only have about 20 papers discussed in class. So, I mean, if you want to continue to work in this area about deep learning, my suggestion is you can continue to read new papers, I mean, from the academia, from the industry, because we have so many papers coming out almost every day, and we have to keep reading all the time. Then we can update our knowledge to know that they are happening right now. I mean, about newest technology right now. Right. So keep reading, keep learning all the time. Then you can, I mean, maintain competitiveness on the market in the future, right? So generally that's for the course. And at the same time, also see that, I mean, right now I just checked the COVID dashboard from UC Davis. I see the case is still increasing recently. I hope you can take care in the summer, and please stay healthy and take care. And also finally, the reminder for the final project paper. I mean, the deadline for the paper will be due by Friday. So please remember the deadline and don't miss the deadline. And if you submit the paper before deadline, generally I think majority of you will get a very good grade with no problem. And I'm not a harsh grader, but if your quality of the paper is not very good, then probably we will have some points deducted. I mean, we will grade the paper according to the novelty, technical depth, and also the research values, right? In several different perspectives mentioned in the syllabus, also in the first class slides. Yeah, so generally that's it. What I plan to say to you in the next course. Thank you so much again, for your help and the efforts time to make this course possible. And I also learned a lot from your presentation as well. Thank you so much. Yeah, any more questions from the students to the presenter or for me?
I have a short question about the project. So
yeah, sure.
Does the length of the paper include the references, or just like references are excluded, just like additional to the 10 pages?
So the paper length is 10 pages, including all the references, also the main contents. If your paper is longer than 10 pages, I can give you extra pages for the appendix with no limitations of the page length. So the main paper will be 10 pages and we will grade according to 10 pages. If you have extra material, you can put it into the appendix with no problem. But our grading will be for the first 10 pages of the main paper.
Okay, so just like, for example, if we have like almost a page of like references, then the rest of it should be like 9 pages, then 9 pages wouldn't be a problem. Okay.
Yes.
Great, thank you.
Yeah, any more questions for this paper and or for this course? This is another opportunity for you to ask questions. You need to take the chance. If there is no other questions, then thanks so much again for your time and efforts to this course. So please keep reading, keep learning all the time. And if you have any more questions, please let me know. You can send me emails or can schedule some extra time for the office hours with me with no problem. Yeah, thanks so much. That's all the things that presented for today. Thanks so much, everyone.
You're welcome.
Okay, so probably that's it for today's class. Thanks again.